Have you ever wondered what makes a rocket work? And I'm not talking about the complicated mechanics or the intricate plumbing of the different propellants, but rather the fundamentals of why does a rocket make a spaceship go forward or a launch vehicle go up into the air? In this video, we're going to be going over a basic overview of rocket engines, why they are useful, how they work in the vacuum of space, and what makes them so powerful. So let's talk about that. To begin this video, I'm going to start off by discussing two ways that can help you visualize how a rocket engine actually works. And the first one of these approaches requires us to go back in time to the year 1686. Around this time frame, Sir Isaac Newton was publishing his 3 laws of motion. Now, I should mention that these laws are more of a description of things that already existed. It wasn't like he was creating momentum, but rather trying to explain what was happening. And the reason why Sir Isaac Newton is pretty famous in terms of a physicist standpoint is because these laws of motion helped scientists understand or predict what is going to happen in the future. So by using math, they were able to figure out, okay, well, if we drop a ball from this height, how long is it going to take to hit the ground? Or similarly, if we throw a ball off a cliff, how far is it going to go? These are some pretty simple questions in physics nowadays. However, back in 1686, this was a breakthrough in science. But what does any of this have to do with rocket engines? Well, Newton's third law is every action has an equal and opposite reaction. Now, typically when people say that nowadays, they aren't referring to physics, but rather behavior such as karma, meaning any action you have will have an equal and opposite reaction. However, Newton's third law applies to everything in physics, or nearly everything. Now you might be wondering, what does that mean? If there's a force, what do you mean there's an opposite force against me? And a perfect explanation is if you were to stand up on the ground. If you're just to stand up, your feet are exerting a force into the surface that you're standing on, whether it be the floor or outside on the ground. And similarly, the ground is going to be applying the same force up against your feet, which is what your feet feel when you're standing on the ground. Now, if the force wasn't equal, then that means you would end up either be breaking through the ground or the ground would be pushing you up into the air. But since Newton's third law stands, that means that all forces must be equal and opposite as long as they're in equilibrium. But we're not going to get any further than that. So again, what does this have to do with rocket engines? Any kind of rocket engine requires some form of propellant or exhaust to be forced out of the back of the rocket nozzle. Let me say that one more time, forced out of the back. Now, because of Newton's third law saying every action has an equal and opposite reaction, since the rocket engine is forcing the thrust out, there must be an equal and opposite force pushing on the spacecraft. And normally, the force pushing on the spacecraft is called thrust. So a rocket engine's thrust is dependent on how fast or how basically forceful you can push the exhaust out of the back of the rocket. So that's one way of trying to understand how exactly a rocket engine works. But there is another way that can help you visualize what's going on. And this is through something called the conservation of momentum. Now, I know usually when someone says something like the conservation of momentum, you want to click off of the page because we're going to get into a lot of physics, but I'm going to try and keep it fairly simple for this case. First, let's describe momentum. And in physics, there are plenty of equations that can do that. However, in this video, we're just going to try and visualize what it means. And typically, when people think of momentum, they think of something that is large or traveling very fast and therefore has a high momentum, or something that's hard to stop. And really, that's essentially the same thing. A large semi-truck that's traveling at maximum speed down a highway is going to have a really high momentum, especially compared to maybe a water bottle that's just slowly rolling down the highway. Meaning that if the semi-truck hit the water bottle, what do you think is going to happen? Well, obviously the semi-truck isn't going to stop, and the water bottle is just going to go flying somewhere. So essentially, momentum is just dependent on the size of the object and how fast it is traveling. So now that we know what momentum is, what is the conservation of momentum? In physics, the conservation of momentum means in a closed system where no energy is dissipated, momentum is conserved across all objects through any impacts or interactions whatsoever. However, we don't really want the physics definition right now. We just want to try and understand what this means. And one way that we can understand this is through an object called Newton's cradle. I have a Newton's cradle right here. And the main idea is that there are 5 small metal balls about the same size suspended by these strings. And if you let go of one of the balls, the momentum is conserved through all the objects and returns back. Similarly, if we continue to do this, we can see that some energy is lost through some of the other balls, but the main idea is that they come through each other and continue to go. Now over time, since we don't live in a perfect theoretical world, friction and noise cause these to slow down and the momentum is dissipated into energy. However, for our case, the main idea is that momentum is going to be conserved throughout objects interacting with one another. Now that makes sense in terms of multiple objects hitting each other, but what happens when an object breaks apart? Well, that's how we can envision a rocket. A rocket, or a rocket engine, is essentially one thing that has a lot of propellant inside of it. And eventually, what ends up happening as the propellant is shot out of the back, small bits and pieces of it are being flown through the rocket nozzle. And as those small bits and pieces are being flown back, we know that momentum has to be conserved in the system. So if we shoot a very small object that way, going really fast, since momentum has to be conserved in the entire system, that's going to cause the spaceship to go the other way, or go forward. So very similar to how we thought about it with Newton's third law and equal and opposite forces, the conservation of momentum essentially says, if we keep throwing things behind us, or if we keep shooting things backwards, eventually we're going to have to go the other way due to the conservation of momentum. The same thing can be done here on Earth. If you're on ice, in a kayak, or even on a skateboard, you can throw a heavy object in front of you, and what will end up happening is you will start moving backwards, just because momentum has to be conserved. Now I should mention that if you're still having a hard time understanding these concepts, you shouldn't be concerned. Normally in a college level physics class, these concepts are studied for multiple weeks or maybe even months. So by trying to learn a brand new concept in a few minutes within a YouTube video isn't probably going to be the same. However, a fun fact is that these two concepts are mathematically similar to each other, meaning that they come from the same math even though they represent two physical different things, which is rather interesting to think about. So now that we've talked about some of the fundamental physics regarding how rocket engines work, we can discuss some of the different categories regarding these rockets, or essentially how they create their thrust. And in this video, we're essentially going to do a very brief overview of this topic, because each one of these categories could include multiple videos going into much detail on how they actually work. But a brief overview is that there are a few different main types, being physical rocket engines, electrical, chemical, thermal, and nuclear. And as you can probably guess, nuclear rocket engines rely on nuclear or radioactive propellants. Chemical relies on the chemical combination or combustion of the rocket propellants that are being used. Electrical provides on some electrical power source. Thermal is dependent on a temperature change. And physical is depending on how you initially create this propellant, or essentially how you pressurize it. So once we launch, if you have a pressurized fuel tank, that essentially is just holding that physical energy. So really, these different categories are just different types of ways that we can store energy and then release it into some form of thrust or exhaust. But again, as I mentioned, each one of these topics could have multiple videos going into much detail regarding how they work. So if there's any of them that you personally find interesting, let me know in the comments below. For the rest of this video, we will talk about chemical rocket engines, which are normally the most popular types of rocket engines since they are commonly used on launch vehicles. So what is a chemical rocket engine? Essentially, it relies on chemical energy, or the combination or combustion of certain types of chemicals. Now, if you have a gas-powered car, your car engine is basically a chemical engine, just not a chemical rocket engine. You put gasoline into the fuel tank pumps it into your engine, and then through many little tiny explosions, you convert that chemical energy into kinetic energy or physical energy, which drives your car forward. Similarly, rocket engines use the stored propellant or stored chemical energy to then be converted into thrust. So although there's a major difference between the design of a car engine and a rocket engine, they are still essentially going based off of some of the same fundamental physics, meaning that they're trying to convert chemical energy to kinetic energy or physical energy. Now, even within chemical rocket engines, there are many types of ones available, including solid rocket motors, which rely on burning solid rocket fuel, or liquid rocket engines, which essentially rely on some combination, again, of different propellants. A biprop engine, or a bipropellant engine, is essentially what the name sounds like. It uses two different types of propellants. But in most cases, it's something like kerosene and an oxidizer. Now, some of the more popular rocket engines that people like to talk about in the industry, such as the Space Shuttle main engines, the SpaceX's Merlin engines, or BE-4, are all bipropellant engines. So that's just something to take into consideration when people are talking about these different types of rocket engines. The last thing I want to talk about in this video are rocket nozzles. And this is a concept that can go from a pretty simple explanation to complicated aerodynamics really quickly. So in this video, I'm going to stay on the simpler side, and if you have any additional questions, let me know in the comments below. But the main idea behind a rocket nozzle is that we're trying to use the explosion we're creating within our rocket engine. Because when we combust these different chemicals, essentially we're just creating a controlled explosion. And how big our rocket nozzle is going to tell us how much pressure or how fast we can depart from the rocket engine itself, meaning that we can create the nozzle at the perfect size. However, there's an issue. When we fly our rocket engines, normally we're starting from sea level and going all the way up into space, meaning that we have to design our rocket nozzle for one pressure or one atmospheric pressure around us. Because since we're going from Earth's atmospheric pressure to a vacuum, we might have to change the design of our rocket engines or our nozzles. And a perfect example of this is SpaceX's Merlin engine. They have different designs for when it's on the ground and when it's in space. When it's on the ground, the rocket nozzle has a diameter of around 0.9 meters, whereas when a similar rocket engine has a nozzle in space, it has a diameter of over 3 meters. And this is because when the engine is in space, they can actually utilize more of that explosion or of the exhaust and allow the exhaust to expand more to create more thrust. So the main idea is you have to be careful about how you design your rocket nozzle, especially if you're flying through the atmosphere, because you could design it to be the most efficient or the most optimal at different locations or different altitudes above the surface. Whereas if you're just flying it through the vacuum of space, you could design it to be most optimal in a vacuum. If you learned something from this video, let me know in the comments below. I'd love to see what people are gaining from this educational content. In the next video, we will be doing a deep dive into SpaceX's Raptor engine and discussing a lot more of the technical details regarding the design. But with all that being said, thank you for watching, and I hope to see you in the next one.